Hi everybody. So welcome back to my channel. So in the last video I have discussed about the unit 1 non-ideal IV effects, in which I told some of the parameters that were the causes for the non-ideal IV effects. So in which we'll continue to the next video, that is about the static logic gates. Especially it is from the unit 2, it's a combinational logic circuits. Hope the topic would be very interesting, and it's also an important topic. So here I'm having the PowerPoint presentation for the topic. So let us discuss about the static logic gates. Actually, what is meant by static and dynamic? So preferably you should know the differences between the static and dynamic, so that only you can able to understand the topic in a perfect manner. So what is static? Static means what? Dynamic means what? So simply in a one word we can say that static is mean stagnant. That is nowhere it would be moving. Just simply placed in a particular point, and it does not allow to move from one place to another place. Simply it is in inactive condition. It means that when you compare with the dynamic is actually it is very actively moving from one place to another place. Dynamic in the sense it is a movable, whereas the static is a stagnant, it does not move from one place to another place. So within this concept, within this thing, you keep it just in the mind. I'll be starting with the subtopics that are given under the static logic gates. First one is the bubble pushing. The bubble pushing followed by the compound gates, input ordering delay effect, asymmetric gates, skewed gates, PN ratios, multiple threshold voltages. So these all are some of the subtopics that would be given under the static logic gates. First one is the bubble pushing. What is mean by bubble pushing? So you know that in the first unit itself, you might have learned that the NAND and the NOR implementation, in which you used to put the bubble at the input side as well as the output side. So depending upon the nature of the circuit, the bubbles have been used either at the input side and at the output side. So in this bubble pushing, the same thing is going to happen. So look at the left side, the diagram is explained about the bubble pushing. In which it means that the first one is about the NAND gate is similar to that of the OR gate. When the bubbles are kept at the output of the NAND gate, is like that the input is having the bubbles at the NOR gate. And similarly, the NOR gate is equivalent to the NAND gate, where the bubbles are kept at the input side. Okay. So with this help, I'll be explaining the bubble pushing the concept. Simply just consider any circuit. Here I am having the circuit where two AND gates are connected in parallel to the OR gate. That is y is, let us put some variables over here, a b c d, like that. So y is equal to a b and c d. Just this is a simple concept, this is a simple expression of the first diagram. Here I am going to implement the bubble concept like that, which means the NAND, in the left side how it is mentioned that the bubbles are kept at the NAND gate. Similarly, I just put an inverter, because whenever you are putting the bubbles at the output, the inverter has to be used at between the terminals. So this is a rule. So I'm putting an inverter, and the bubble and the inverter both are cancelled, and finally you'll be getting the AND gate. So I'm just putting in a reverse way. That is inverter towards the NAND gate, and also inverter at the output of the NAR gate. So finally, the C, I'm just taking out the bubbles uh, with the help of the left side diagram, and finally I'm getting the diagram like this. So this is the bubble pushing. So in this means the transmission of the circuit diagram is in a static manner. The next one is about the compound gates. Compound gates means using many number of gates. Compound, you know that always meaning that compound having meaning of using a more number, like that. For example, an expression is given that y is equal to ab plus cd whole bar. So instead of whole bar, I'm just putting the dash. I'm drawing the diagram for the ab cd by using the pmos and the nmos. How it is looking like. The figure A represented the A, B, and C, D. is similar to that of the figure B, AB, and C. I'm just connecting towards the A and B terminals with the C and D, AB and CD. And finally, the D diagram represents the complete AB and CD. Similarly, for the above expression, I usually put the AB and CD like that. How to say that? For the dot, which means that for the product, the PMOS would be is an always parallel, and whereas the NMOS in a series condition. Similarly, for the series, that is plus, the PMOS is always in series condition, and whereas the NMOS is always in the parallel condition. With the help of this thing, I concluded the diagram, and finally I obtained the diagram F. Next one is the input ordering delay effect, which means that by ordering the input, I am getting the delay effect. The logical effort and parasitic delays are different gate inputs is often different. So here in the circuit, A and B are having two with a mass transistor, capacitor, and capacitor value of 2. Here, if I am ordering the input, that is first one B and the second one as a, I'll be getting the delay output. So this is the input ordering delay effect. Once if it is designed, it will be keep on in the same manner for any kind of logic circuits. If the input arrival time is known, connect latest input to the inner terminal. Right. The next one is about the asymmetric gates. When one input asymmetric and symmetric, which means that symmetric means having both are same appearance. Like for example, if you take a butterfly as an example, when you break it over into two halves, the both the halves are similar. So that is said to be as a symmetric. And similarly, when the break in some other example, for example, if you take an amoeba like the protoplasm, like that, they are in a regular shape. If you break into two halves, the both the halves are dissimilar to each other. So those things are said to be as a asymmetric or asymmetric. So here similarly, the transistor are said to be an asymmetric gate. When one input is far less critical than the another, even nominally symmetric gates can be made asymmetric to favor the late input at the expense of the early one. Right. So here some of the values have been mentioned, but it is not given in the presentation. Just replace it with any kind of values. Right. Next one is the skewed gates. What is meant by skew? The even value of PMOS and the NMOS, it should be 2:1 ratio. So that is the value of. If it is not like that, then it would be given as either high skew or a low skew. For example, the middle diagram is having a unskewed inverter, that is the ratio is 2:1. If the ratio is exactly 2:1, then it is to be as a unskewed inverter. For the left diagram, it is considered that the ratio is 2:1 by 2, which means that the ratio is not in the proportion of 2:1. So these are said to be a high skew inverter, whereas 1:1 by 2 is also said to be as the low skew inverter. So these are the three types of skewed gates we are often studying in the VLSI design. Then P-N ratio. In general, best P-N ratio is square root of equal delay ratio. Only improves average delay slightly for inverters, but significantly decreases area and power. So by putting exactly the P-N ratio, we can we can get the above application mentioned, that is significantly decreases the area and the power. So here there are three diagrams were given about the P-N ratio, in which the most fastest one is about the inverter, then NAND, and as well as the NOR. The last one is the multiple threshold voltage. Some CMOS multiple threshold means that for a CMOS transistor, there is only one threshold voltage, that is absolutely the value of the threshold voltage is Vs is equal to 0.7 volt. But for the multiple threshold voltages, here many number of threshold voltages have been given, so that the further processes are easily acceptable. But how far this is implemented in real time is not uh, exactly known. Right. Some CMOS processors offer two or more threshold voltages. Uh, Transistor with lower threshold voltages produces more on current, but also leak exponentially more of current. Lower threshold gates can be used to reduce delay of critical paths. And finally, skewed gates can use lower threshold devices on only the critical network of transistors. So these all are the things that would have been discussed under the static logic gates topic from the second unit. So I'll be concluding with this, and if you're having anything doubt regarding this topic, feel free to text me within the comment box. Just put it over the comment box. I'll be checking and give you more explanation about the particular topic. So thank you all for watching again. Just keep in touch with me for any outcome. I'll be taking the class regarding this VLSI design would be very useful to you. Okay, thank you.